Here's my second video over nonlinear systems, and we're going to work two examples in this one. And we're going to start by solving a system of equations graphically. And you can see we have a nonlinear system here because this is the equation of a circle, and we'll talk about how to graph the circle in a minute. And this looks like an absolute value equation, so we're going to talk about how to graph that as well. And so as I look at this, if I look at the equation of my circle, if you're not sure how to graph a circle, I would encourage you to go watch my videos over how to graph a circle. But basically, the equation of a circle is x minus h squared plus y minus k squared equals r squared, where hk is the center of the circle. Meaning in this one, it doesn't really show an h, so it's 0. And our equation doesn't really show a k either, so it's 0. In other words, x minus 0 squared is the same thing as x squared, and y minus 0 squared is the same thing as y squared. And then lastly, that's going to be equal to our radius squared. And since this says 16, that means r squared is 16, so our radius is 4. So if I wanted to graph that, I put my center of the circle at 0, 0, which is our hk. That's the center of our circle. And then I do my radius of 4. So I've got 4 in all directions. I'm going to do my best to graph this circle here. And boom, you got to circle through all those points. Now, as I look at this, it looks like we got an absolute value equation. So if I were to solve this and get the y by itself, and hopefully we can think of this as a transformation to the absolute value parent function. And how this is transformed, it looks like it's our absolute value parent function, but it's going to be reflected, okay? And then it's going to be shifted up 4 units. So instead of starting at the origin, because most absolute value functions kind of start at the origin and go like that, or at least the parent function does. So what we've done is we've shifted it up 4 units to start here, and then because of the negative, we've reflected it. And so it's still kind of got that slope of -1, and it's going to go that direction, and it's also going to go that direction, okay? And now we can see what the solutions are. Because remember, our goal here was to solve it graphically, so we're just looking for where these intersect. And it looks like that's going to intersect once there, and once there. So this system of equations actually has 3 solutions. It has the solutions -4, 0, which we show right there. Then it has 0, 4. 0, 4. And then lastly, okay, so because here's 0, 4, and then lastly it has 4, 0. So before we jump into our next example, just to recap, I can solve a system of nonlinear equations by graphing them. And you got to be good with graphing your parent functions. You got to be good with graphing circles. You got to be good with graphing absolute value functions. But once you graph them, just like with systems of linear equations, those points of intersection are the solutions. You can have all sorts of different numbered solutions: 1, 2, 3, 4, so on and so forth. All right, let's look at another example. And so this says solve the system of equations algebraically and graphically. And so we've got this system here. And so I think I'm going to start off by solving it algebraically. And let me start by going color-coded, because whenever we solve systems, it helps to have them in certain colors. So I've got the first one in blue, and it looks like this is probably going to be a quadratic. It's definitely going to be a quadratic. And then we've got this second linear equation in red. And so I'm just going to substitute. Since I have y isolated in my second equation, I'm just going to substitute that in for x in my first equation. So we have x plus 2 squared equals y plus 5. So hopefully you see that I just took the y that's right there and substituted in 3x plus 5 for it, since from our other equation we have that y equals 3x plus 5. And so now I've got an equation with only x, and we can solve this. So on the left side of my equation, I'm going to distribute that out, which that's going to be x plus 2 times x plus 2. Anything squared is that value times itself. And if I were to distribute, that would be x squared plus 4x plus 4. And that's going to be equal to 3x plus 10 once I combine those like terms. And now since we've got a quadratic, when we solve quadratics, I'm going to collect all my terms onto the same side of the equation. So I'm going to subtract 3x from each side. And then I'm going to subtract 10 from each side. And now we've got a quadratic that we're ready to solve. From here, I'm just going to solve by factoring. You could solve with quadratic formula if you're not comfortable with factoring, but it looks like it's not going to be too tough to factor. So what I end up with is I end up with the solutions, or I should say the equations, x plus 3 equals 0 and x minus 2 equals 0 by the zero product property. So x equals negative 3 and x equals positive 2. So that's a lot of algebra right there, but what that tells us is that our solutions are going to take the form of negative 3 comma blank and 2 comma blank. And so our way that we find the y coordinate that goes with these x's, because keep in mind these are both x values, right? It's not that one is an x and one is a y. It's that they're both x values. It's looking like we're probably going to have two solutions to our system here. And so what I do is I just take my negative 3 and substitute into this function. 3 times negative 3 is negative 9. Negative 9 plus 5 is going to be negative 4. I'll go with green. And then when I substitute a 2 in, 3 times 2 is 6. 6 plus 5 is 11. So it's looking like my solutions are going to be at the points negative 3, negative 4. So I'm hoping my lines intersect there. But I'm also hoping they intersect at the point 2, 11, which is just off my graph. If I remember right, this graph goes up to 10, so that would be an 11. So pardon me for going off the graph. But now let's graph these two and let's see what they look like. I think the easier one to graph is going to be that linear function. So let's graph it first. It has a y-intercept of 5 and a slope of 3. So I can kind of see it's going to go through that green dot up there. I can see it's going to go through this green dot down here. And that's going to be our linear function, okay? And graphing the quadratic might be a little bit tougher. Let me just come down here. If I were to graph it, if I were to rearrange it, I'd subtract 5 from each side. So if I subtract 5 there and subtract 5 there, you'd have this, y equals x plus 2 squared minus 5. And maybe we could think of this as a transformation to the quadratic parent function. I'm assuming you have an understanding of how to graph a quadratic out of vertex form. But it looks like we're going to shift our quadratic parent function 2 units to the left and 5 units down. And I'll write that, 2 units to the left and 5 units down. If I were to do that, if I were to take it from the vertex over, and we're going to go 2 to the left, and we're going to go 5 down, okay? That's going to put my vertex right here, which means if I was graphing my quadratic, it would look like this. It would look just like this, boom, and boom. And so moral of the story is we started off by solving algebraically and we got two solutions. One's there and one's there, okay? We got it from those 2 points, but then also we can just graph with these. If these are equations that we feel comfortable graphing, I can just graph the lines and see where they intersect. It's kind of hard because every problem is going to be different depending on what type of nonlinear equation you have. You could have a cubic, you could have an absolute value, you could have a circle, so on and so forth. So every problem could be different, but if you understand the general ideas of how to solve with substitution and how to graph, you should be good.